Okay, so we've talked about centrality, dispersion, and going back to, the original, the first lecture, we talked a little bit about skew and kurtosis. And I'm going to kind of just the last little video, I'm going to expand some of that stuff, look at some examples, and then ultimately do a couple of calculations. Okay, so remember we talked a little bit about this. This is positive skew. So a good example would be income inequality. A distribution of incomes. You've got a lot around this here, but you're going to have a few people with very high incomes. So something like incomes, house prices would show positive skew. Negative skew, maybe exams, exam grades, and the example data set I have is a database of cleanliness scores of ships. Wherever there's a standard where most people meet the standard, but there's kind of a tail of the left side, that's a good example of negative skew. And kurtosis, we really, really rarely use kurtosis in research, but it's just kind of this idea. You've got a thin distribution. You can't see it here, but it's got relatively thicker tails. Then that's leptokurtic. It's got positive kurtosis and negative kurtosis, which is kind of more almost a bit like a normal distribution, but thinner tails. That's platokurtic. But there's no way I'm going to ask you those names on exams or anything like that. So going forward a little bit, stuff we missed out. One way of understanding skew is if we have positive skew, the mean is greater than the median, which makes sense. So consider a distribution of incomes. We add one item to that distribution. That item is Bill Gates or somebody earning $1 billion that year from selling all their tech stocks. Adding that $1 billion is going to make the mean go to the right, maybe quite significantly if it's a smaller sample. But it's only one additional observation to the right of the median, so it's only going to shift the median up like one place. It's only going to shift the median very, very small. So if you have this right skewed distribution, then you will have the mean greater than the median. If the data is symmetric, then the mean is exactly equal to the median because the mean is in the center of the distribution, the median is in the center of the distribution. And a similar thing skewed left, but this time the mean is less than the median. So again, we have all of our, maybe I'm being too nice and I've got lots of scores around 80, 90, and somebody just turns up and writes their name and gets like 1. That person is not going to affect the mean very much because it's just one person to the left. So it's not going to affect the median very much because it's one person to the left, but it is going to quite strongly affect the mean when all the other values are in the 80s and 90s. So here's a nice example, actual real world example. So this is actually when we talk about income inequality, we have the average income going up in this blue line and the median income going in the red line. And you can see that the mean is going faster than the median. And these little diamonds are showing the ratio between those. And you see that the ratio of the median to the average is declining over time. The median income is now only 65% of average. So you can actually use that as a measure of income inequality. If you see that the mean is much higher than the median, the higher the mean is than the median, the more it's skewed by extreme values, then the higher the level of inequality. So this is a fun thing. I said salaries tend to be right skewed, but we have some salaries here. And this is basically salaries of business majors going into industry. And you can see the means are almost exactly the same as the medians. So what's going on here? Am I talking rubbish? Well, I'm not talking rubbish, but the idea is that these are all salaries of fresh graduates. And fresh graduates tend to be on the scale. There's very few fresh graduates earning $1 million. At least not in this sample. These are all kind of standard corporate entry-level positions, which is why in this case, the salaries for these positions are probably relatively normal. So here's like these three examples. And this is, I did these in R, but I'll just show you them in SPSS. Again, just to get going with SPSS a little bit more. So we got SPSS. Let's look at some of these examples. So let's open data. And we're actually in Excel files. And the first thing we have is we have R&D. And this is research and development spending. Just give it a second to load. Okay, so this is research and development spending, the amount of, the revenue they spend on research and development of, kind of a number of corporations. Now let's just analyze this. So let's analyze descriptive statistics. And let's do explore. And we're just going to put this in the dependent list. And statistics, we're just going to have the standard descriptive statistics. We're also going to plot. We're going to have, we're not going to worry, we're going to have a histogram. We're not really, we'll do the normality plot, but we won't go into that at the moment. Click OK. Okay, so let's just have a quick look at this output. And you can see here on this data, the mean is greater than the median. The mean is 8.5 and the median is 8. And you can kind of see why, it's just not quite normal. And there's this little cluster of companies up here that have a much higher research and development percentage. So not extreme, not like the income, but this is positively skewed. And what the normal QQ and the detrended normal QQ plot is, they assume that if you have a standard normal distribution, that all of these points will be on the line. If the points were normal, they would be on the line. And how far off the line they are is how far away from the normal. Again, you see some of the points to the right are a little bit off the line. Okay, so the second example, we can see that one was right skewed. The next example, I'm going to load in another data file. And I'm going to load in one called the sanitation scores, which we talked about. And here you can see this is actual data. So these are actual cruise liners and how much they got on the sanitation scores. Remember, most of these are in the 90s, but we've got a few in the 60s like this one. So never actually travel on the VM ships, leisure, SAM. Go to graphs, chart builder. Sorry, I still think I'm on last week. Go to analyze, descriptive statistics, explore. And we're going to do it on the score. We put into the dependent variable list. We just want the basic descriptive statistics and then plots. We'll just have the histogram with the normality plot. Click OK, click OK. And you can see here, we have the mean is 95 and the median is 97. So here the mean is less than the median. It's not extreme. But here you can see this negatively skewed data. Now, funnily enough, I'm not going to play around with the bars. We've had long videos it is this week. But the reason we have one that looks like over 100 is we just have a histogram bin that's probably got 100 as its lower bound. We really, if I was playing around, I should correct with that because that just looks a bit silly. But overall, we've got this negatively skewed distribution with a lot at the high end and then a few kind of outliers around 70. And again, you can see on the QQ plot, you can see the outliers at the bottom of the distribution. Okay, and then finally, And you can also see, I forgot to mention, with the other one, you can actually get a negative skewness coefficient there, which we're going to calculate in a minute. The one we had previously had a positive skewness coefficient. Okay, so the third data file is our corporate sustainability scores. And here, these are basically, it was just from a Likert survey of accounting managers where they ranked their company in terms of corporate sustainability, and each company got a score, a sustainability score. And let's just have a look at this distribution of scores so we know exactly the same as before. I don't need to explain it now. Okay. Okay, and we have very slightly negative skewness, and the mean very, very slightly less than the median. So it's pretty much almost normal. And you can see the histogram here. Look, it looks pretty normal. You've got maybe one or two tiny outliers here and a little cluster of maybe outliers down there. And you can see again, this is amazingly close to the normal QQ plot here. Okay, so to finish off, so we've talked about all the main concepts. I just want to kind of just show you the calculations for skewness and kurtosis. So let's kind of go back to the whiteboard. Let's just start something new here. Okay. So the formulation for skewness, and this is for the population. You have n-1 version for the sample, but we'll just stick with the population, as this is not really something, I don't think you're ever in your research career is going to calculate skewness by hand. So it's each observation. Sorry, xi minus mu. My pen seemed to stutter on the xi. Cubed all over n, and then the standard deviation cube. Now the important point here is this is to the power of 3. So if xi minus mu is negative, then this is going to be negative. Then this is going to be negative. Is also going to be negative. I don't know what is happening with my pen. And if it's going to be positive, then to the power of 3 is also going to be positive. So when you have a really large, a really big now value of this number, so if you have a value a long way away from the mean, so an outlier, a positive or negative, if that outlier is positive, it's going to give a very big positive value. And if it's negative, it's going to give a very big negative value. So that's why you have these big incomes, right skewed distributions. These big values are positive. If you have like the sustainability, the values on the way for the mean are negative, it's going to lead to a negative skewness. So let's just have a quick example. We have 4 numbers, 2, 3, 5, and 10. What is the skewness? Well, first, let's just calculate the mean. And I'll assume you can work these out by now, so I won't actually calculate these by hand, but that's obviously 20 over 4 is 5. But since we're calculating skewness, we won't go into detail on the standard deviation. So I'll just tell you now that the sigma is 3.082 and sigma 3 equals 29.28. This is actually in the book, this example. And so we can calculate, let's just calculate the sigma xi minus mu to the 3. So the first observation is 2. The second is 3. Second, we've got 5. And the third, we have 10. And you can see here now, that the very large number, kind of the outlier away from the mean, is positive, which is going to give us a positive value. So we have minus 3 to the 3, which is minus 27, plus minus 2 to the 3, which is minus 8, plus 0 to the 3, plus we have 5 to the 3, so 5 times 5 times 5 is 125, which gives us a numerator of 90. And then, so our skewness is going to be 90 all over 4, as per the formula, because that is my value of n, and I have 4 observations. 4 times my sigma cubed, which was 29.28. And then, given that large 125, it's no miracle that we have this positive skewness. Okay, so that's skewness. I just wanted to show you how, the equation related to the concept. If we were doing a more mathy course, we would do this in more detail, and this would actually be called the third centered moment. I don't know why it's being so slow with me. The xi minus mu to the power of 3. Okay, so let's just do kurtosis. So the formula for kurtosis, and there's actually multiple formulas for kurtosis, so you have to be careful. And that's why I'm relatively lenient. But if I give you one on the homework, just use this formula. And you can see here, just again, a little bit of intuition from the equation, that you see we have, basically this is a trade-off here. We have this value to the left and this one to the right. And this is always going to be positive because it's a power of 4. Now, if we have we have quite a few large values away from the mean. So if we have this kind of leptokurtic, with these kind of very thick tails here, then this value is going to be kind of bigger than if we have it with, oh my God, that was a terrible line. We've got the platokurtic. Where it's like, kind of thinner tails. Okay, that wasn't a very good drawing. But the idea is you have less. There's kind of, if this is X bar, you've got less that's far away from the mean. So this guy is going to be much, much smaller. So let's just have one quick numerical example. Same as with the skewness. Okay, so we have 4 numbers. Okay, so we have 1, 5, 7, and 11. And the mean is going to be, I'm going to assume a very small population of something. So the mean we have 18 plus 6 is 24 over 4 is 6. And we've got the sigma squared is 13, which means that sigma to the 4th is going to be that squared. 13 squared is 169, which I think was the last times table I learned as a kid. So let's just kind of go back to the equation. Let's just, so we can see it a little bit. We want sigma minus mu to the 4. So that's going to be, the first one is going to be 1 minus 6 to the 4. Equals, plus 5 minus 6 to the 4. Plus 7 minus 6 to the 4. Plus 11 minus 6 to the 4. Looking very symmetric there. So which is equal to 1 is minus 5 to the power of 4. So it's 5 times 5, 25 times 5, 125 times 5 is 625. Minus 1 to the 4 is 1. 1 to the 4 is 1. And then again, 11 minus 6 is 5 to the 4 is 625. Equals 1252. And so the overall skewness, so the kurtosis, is going to be 1252 divided by n, which is going to be 4, times by sigma to the 4, minus 3, and it's 1.85 minus 3, and it's going to be minus 1.15. So we just about have a negative kurtosis there. Okay, so we have done a lot this week. Any questions, feel free to email me. There was a little bit more math than we've used to in this class, but again, there were some of the real basics that I wanted to get, sorted out, and just having a little bit of intuitive understanding how some of these descriptive statistics works is useful when evaluating your research and looking at data. So there we go. And that's it.